Have you ever wondered what time actually is? Not how we measure it, but what it's made of. Right now, as you listen to these words, time is passing. You feel it moving forward, carrying you from one moment to the next. But what is it that's moving? Is time a river that flows? A dimension like space? Or is it something stranger, something that emerges from the deep quantum fabric of reality itself? Physics can tell you how fast light travels and how gravity bends space. But ask what time is, and the equations fall silent. Einstein showed that time can stretch and compress. Quantum mechanics reveal that it might not exist at the smallest scales. And cosmology suggests it had a beginning, which means it might also have an end. Tonight, as you drift towards sleep, we're going to explore the most mysterious dimension, the one you've lived in your entire life, yet cannot touch, see, or hold. We'll journey from the ticking of atomic clocks to the edge of black holes, from the Big Bang to the heat death of the universe. And along the way, we'll ask the question that has puzzled humanity for millennia. What is time made of? Before we begin, if you're kind enough, a gentle like or a quiet tap on subscribe would mean the world to me. It's a small gesture, but it keeps these quiet explorations alive and reminds me that these cosmic lullabies still find their way to gentle hearts like yours. Now, let's begin with the first question. Part 1. If time flows like a river, why can't we see the current? Time feels like motion, like something flowing past you, carrying moments from future to present to past. We even use water metaphors. Time flows. Events stream by. The past lies upstream, the future downstream. But if time is truly a flow, what exactly is flowing? And if nothing is moving, why does it feel like it is? The ancient Greeks wrestled with this question. Heraclitus said you cannot step in the same river twice, meaning everything changes, everything flows. But his contemporary Parmenides argued the opposite. That change is an illusion, and only being, eternal and unchanging, is real. 2,000 years later, we're still caught between these views. Physics describes time as a dimension, like length, width, and height. According to Einstein's theory of relativity, space and time are woven together into a four-dimensional fabric called space-time. In this view, time doesn't flow. It simply exists, stretched out like a landscape. The past, present, and future are all equally real, existing simultaneously in what physicists call the block universe. NASA's gravity probe, B mission, confirmed that Earth's mass curves space-time around it, just as Einstein predicted. Time near Earth's surface runs slightly slower than time farther away, a measurable effect verified by atomic clocks. This isn't because time is flowing at different speeds. It's because the geometry of space-time itself is warped by gravity. But here's what's strange. If time is just a dimension like space, why do we experience it so differently? You can move freely through space, forward, backward, left, right. But time only moves one way. Forward. Always forward. You remember yesterday but not tomorrow. You can revisit a place but never a moment. This one-directional flow is called the arrow of time, and it's one of the deepest mysteries in physics. The laws of nature at their most fundamental level don't distinguish between past and future. If you filmed an electron bouncing off another electron and played the video backward, you couldn't tell the difference. The physics works equally well in both directions. Yet, in our everyday world, time has a clear direction. Eggs break, but don't unbreak. Coffee cools, but doesn't spontaneously heat up. Living things age. The universe expands. Everywhere we look, time marches forward. But why? The answer may lie in entropy, a measure of disorder or randomness in a system. According to the second law of thermodynamics, entropy always increases in a closed system. Things naturally move from order to disorder, from organized to scattered, from warm to cold. A broken egg has higher entropy than a whole one. Scattered atoms have higher entropy than organized molecules. This increase in entropy gives time its arrow. The past is the direction of lower entropy. The future is the direction of higher entropy. As NASA's Jet Propulsion Laboratory describes it, entropy is time's compass, always pointing forward. But this raises a deeper question. Why was entropy so low at the beginning of the universe? The Big Bang was an incredibly ordered state. Everything compressed into an infinitesimal point. From that moment, entropy has been increasing, spreading, diluting across an expanding cosmos. If the universe had started with maximum entropy, nothing would happen. No stars, no planets, no life. Time would have no arrow. Physicist Sean Carroll suggests that the arrow of time is actually the arrow of entropy. We perceive time flowing because we live in a universe that started in a low entropy state and is gradually unwinding toward disorder. Our memories, our sense of causation, our feeling that time flows, all emerge from this cosmic trend toward chaos. The European Space Agency's Planck satellite mapped the cosmic microwave background, the faint afterglow of the Big Bang. It showed that 380,000 years after the universe began, matter was distributed almost uniformly, with only tiny variations, about 1 part in 100,000. Those tiny variations were the seeds of all structure. Galaxies, stars, planets, and life itself grew from those initial fluctuations. That early uniformity was a state of very low entropy for the matter in the universe. Since then, as galaxies formed and stars ignited, entropy has increased. The concentrated energy of the Big Bang has spread out, diffused into the vast darkness of space. And that spreading gives us our sense of time's passage. But here's what physicists find unsettling. If time's arrow comes from entropy, then time itself might be an emergent property, not fundamental. At the quantum level, where individual particles interact, there might be no arrow of time at all. Only when you have vast numbers of particles, enough for statistics and entropy to matter, does time's direction appear. Take a movie of molecules bouncing around in a box. Play it forward or backward, and the molecular physics looks the same. But zoom out to see the gas spreading to fill the box, and suddenly time has a direction. The gas spreads, never contracts. That's entropy in action. So perhaps time doesn't flow at all. Perhaps what we call the flow of time is just our consciousness moving through a static four-dimensional landscape, encountering moments in sequence because of the way entropy organizes our memories and perceptions. Carlo Rovelli, a theoretical physicist, puts it beautifully. Time is ignorance. What we call the flow of time is not the flow of time itself, but the growth of our ignorance. As we move from past to future, we gain information, we see entropy increase, and we interpret that as time passing. But even this explanation feels incomplete. It tells us why time has a direction, but not what time is made of. Is it a substance, a field, a property of space itself? Or is it something else entirely? Something that only exists in the structure of causes and effects, in the relationships between events. The James Webb Space Telescope peers back in time, observing galaxies as they were billions of years ago. But it's not actually looking backward through time. It's looking across space at light that has been traveling for billions of years. The light is old, but time itself hasn't moved. Time, in the block universe view, is laid out all at once, and we're simply seeing different slices of it. This view is both beautiful and unsettling. If all moments exist simultaneously, then the past isn't gone and the future isn't yet to come. They're just elsewhere in space-time. Your childhood, your old age, even your final moment, all exist eternally in their respective places along your world line, the path you trace through four-dimensional space-time. But if that's true, if time is just a dimension, then why does it feel like it flows? Why do we experience the present as uniquely real and the past as fixed, while the future remains open? These questions have no simple answers, not yet. As you drift towards sleep tonight, consider this. Perhaps time doesn't flow like a river at all. Perhaps you are the river, and time is the landscape through which you move, encountering each moment in turn, carried forward not by time itself, but by the universal increase in entropy, the slow unwinding of order into chaos that began with the Big Bang. Take a slow breath. The present moment you're experiencing now is not a point moving through time. It's a place in space-time where your consciousness happens to be. And as entropy increases, as memories form and moments pass, you slide gently forward into what you call the future. But before we can understand where time is going, we must first ask, where did it come from? And that question leads us backward to the very edge of existence itself. Part 2. Did time have a beginning? If you could rewind the universe like a film, you'd see galaxies rushing together, stars unforming, atoms compressing. Keep going back, and eventually, you'd reach a moment where all of space, all of matter, all of energy existed in a single point. Scientists call this the Big Bang, the beginning of everything. But here's the question that keeps cosmologists awake at night. Was it also the beginning of time? Before Einstein, most people assumed time was eternal, an unchanging backdrop against which events unfolded. Isaac Newton described time as absolute, flowing equably, without relation to anything external. In Newton's universe, time existed whether anything happened or not. It was the stage, and the universe was merely the play. But Einstein changed everything. His general theory of relativity, published in 1915, revealed that time is not separate from space. Together, they form space-time, a flexible, dynamic fabric that bends and warps in the presence of mass and energy. And if space-time is part of the universe, not separate from it, then time itself must have begun when the universe began. According to NASA's Wilkinson Microwave Anisotropy Probe, the WMI, and the European Space Agency's Planck satellite, the universe is approximately 13.8 billion years old. That's not just the age of matter or stars, it's the age of time itself. Before the Big Bang, there was no before. There was no time in which nothing existed. There was simply nothing, not even the nothing of empty space. As cosmologist Stephen Hawking once said, asking what came before the Big Bang is like asking what lies south of the South Pole. The question itself has no meaning. Time and space emerge together in that first instant. There is no earlier moment to reference, no prior cause to identify. This idea is deeply counterintuitive. We're used to thinking of time as a line stretching infinitely in both directions. But cosmology tells us that line has a starting point. Time didn't exist until the universe created it. But how can something begin without time already existing? How can there be a first moment if time itself is what you need to define first? These questions probe the limits of language and logic. We're asking about a state where time itself is part of what needs explaining. One way to think about it is to imagine time emerging gradually, like the surface of the ocean forming from mist, in the earliest fractions of a second after the Big Bang, during what physicists call the Planck epoch. Time and space were so scrambled by quantum fluctuations that they had no clear meaning. Time, in the way we understand it, didn't fully exist yet. Quantum gravity, the still theoretical merger of quantum mechanics and general relativity, suggests that at scales smaller than the Planck length, 10 to the power 35 meters, and shorter than the Planck time, 10 to the power 43 seconds, the smooth fabric of space-time breaks down. It becomes a foaming, fluctuating quantum mess, where cause and effect lose their usual order. In this quantum foam, time might not flow forward in a straight line. It might loop, branch, or exist in superposition, multiple timelines overlapping. Only as the universe expanded and cooled did time settle into the smooth, one-directional flow we experience today. This is where the Big Bang becomes more than just an explosion. It's a phase transition, like water freezing into ice. Before the transition, the universe was in a state where time and space were unified and inseparable. After the transition, they separated into distinct dimensions, with time taking on its familiar forward-moving character. NASA's James Webb Space Telescope has observed galaxies that formed just 300 million years after the Big Bang. These galaxies already show structure, rotation, and chemistry. Time, by that point, was fully operational, ticking forward with the rhythm we recognize. But in the first instance, time was still forming, crystallizing out of the quantum chaos. Some cosmologists propose that time might be cyclic, that our Big Bang was not the absolute beginning, but rather the latest in a series of cosmic rebirths. In these models, the universe expands, contracts, and bounces back in an eternal cycle. Time, in this view, has no ultimate beginning or end, only phases. But current observations don't support a cyclic universe. The discovery of dark energy, the mysterious force causing the universe's expansion to accelerate, suggests that the universe will expand forever, not contract. According to measurements from the Hubble Space Telescope and the Supernova Cosmology Project, the universe is not only expanding but speeding up. This rules out a simple bounce scenario. Still, the question of time's origin remains open. Loop quantum gravity. One approach to quantum gravity suggests that the Big Bang might have been a big bounce, a transition from a previous contracting universe. In this model, time would extend infinitely into the past, though each cycle would reset the clock. String theory offers yet another possibility. In some versions, our universe is a three-dimensional brain floating in a higher dimensional space. Time in this picture might exist in those extra dimensions, with the Big Bang marking not the creation of time, but its entry into our observable universe. These ideas are speculative, but they highlight how uncertain we still are about time's nature. What seems certain is that time, as we experience it, is tied to the universe's evolution. Where there is no change, no events unfolding, no entropy increasing, there is no meaningful time. The European Space Agency's Gaia mission has mapped over 1.8 billion stars, tracing their motions backward to reconstruct the Milky Way's history. By understanding how galaxies evolve, we glimpse how time itself is woven into cosmic structure. Every star's light carries a timestamp, a record of when it was emitted. Time is not just passing, it's accumulating, building up layers of history. If time had a beginning, it must also have properties, characteristics that define what it is. But the Big Bang doesn't tell us what time is made of, only when it started. To understand its substance, we need to look deeper into the quantum realm where time becomes something far stranger. As physicist John Wheeler once said, "Time is what keeps everything from happening at once, but perhaps that's only half the answer." Perhaps time is also what emerges when enough events happen that they can be organized into a sequence. And that sequence, that ordering of cause and effect, is what we mistake for a flowing river. Take a slow breath. Right now, you exist in a moment that is 13.8 billion years downstream from the Big Bang. Time didn't exist before that moment, and yet here you are, carried forward by entropy's gentle current, living in a universe where past and future have meaning because time itself was born. But if time had a beginning, does that mean it will have an end? And if time can stop, what would it mean to exist in a timeless state? That question leads us forward into the strange territory where time itself begins to dissolve. Part 3. Does time exist at the quantum level? Imagine shrinking down smaller than an atom, smaller than a proton, down to the Planck scale, the smallest meaningful distance in physics, 10^35 meters. At this scale, space and time lose their smoothness. They become grainy, discontinuous, like pixels on a screen. Here, in the quantum realm, the familiar rules break down, and time, the steady march of seconds and minutes, might not exist at all. In classical physics, time is a parameter, a background variable that measures change. You can plug it into equations to predict where a planet will be or how fast a ball will fall. But in quantum mechanics, time plays a different role. It's not an observable property like position or momentum. You can't measure time itself, only changes in time. This distinction matters because in quantum mechanics, observables correspond to operators, mathematical objects that represent measurable quantities. There is no time operator. Time is not something you can observe directly. It's a label, a way of ordering events, but not a thing in itself. Physicist Carlo Rovelli, one of the founders of loop-Puy quantum gravity, argues that time might be an illusion, an emergent property that appears only at macroscopic scales. At the fundamental level, he suggests, the universe is timeless. Events happen, but they don't happen in time. They simply are, related to one another through quantum correlations. This idea challenges everything we feel intuitively. How can there be events without time? How can anything change without a clock ticking forward? The answer lies in relationality. In quantum mechanics, systems are defined not by absolute properties, but by their relationships to other systems. An electron doesn't have a position until it's measured relative to something else. Similarly, time might not flow universally, but emerge from the relationships between events. NASA's experiments with atomic clocks aboard satellites have shown that time is relative, not absolute. A clock in orbit ticks faster than one on Earth's surface because it experiences weaker gravity. This is gravitational time dilation, predicted by Einstein's general relativity and confirmed to extraordinary precision. Time, it turns out, is local, not universal. Every point in space has its own clock, running at its own rate, but quantum mechanics goes further. In the famous Wheeler-DeWitt equation, which attempts to describe the quantum state of the entire universe, time disappears entirely. The equation is static, describing a timeless quantum state. Change, in this view, is not fundamental. It's an approximation that emerges when you zoom out and look at subsystems within the universe. This timeless picture is unsettling. It suggests that the flow of time we experience is a kind of perspective effect, like the way a two-dimensional creature might perceive a three-dimensional object. We see time passing because we are embedded in the universe, experiencing it from within. But from the universe's point of view, if it has one, everything simply exists, unchanging and eternal. The James Webb Space Telescope observes distant galaxies whose light has been traveling for over 13 billion years. But the photons themselves, From their perspective, experience no passage of time. At the speed of light, time stops. A photon emitted at the Big Bang and one emitted yesterday exist in the same eternal now. Only when they interact with matter, when they are absorbed or reflected, does time begin again. This is one of the strangest predictions of relativity. For anything traveling at the speed of light, time does not pass. Distance collapses to zero. The journey from one side of the universe to the other takes no time at all. Only for observers moving slower than light does time flow. At the quantum level, this gets even stranger. In experiments with entangled particles, two particles can be correlated in such a way that measuring one instantly affects the other, no matter how far apart they are. This phenomenon, confirmed by countless experiments and central to quantum mechanics, seems to violate the flow of time. The effect happens instantaneously, without any time passing. Einstein called this spooky action at a distance and never fully accepted it. But experiments, including those by Anton Zeilinger, who won the Nobel Prize in 2022, have proven that quantum entanglement is real. The universe, at its most fundamental level, does not respect the strict separation of past, present, and future that we take for granted. Some physicists, including Don Page and William Wooters, have proposed that time emerges from entanglement itself. In their view, the universe as a whole is in a single timeless quantum state. But when you divide the universe into subsystems, observer and observed, time appears as a way of organizing the correlations between them. This idea is radical. It suggests that time is not a fundamental feature of reality, but an emergent phenomenon, something that arises only when you have separate systems interacting and becoming entangled. In a perfectly isolated system, time would have no meaning. Only in a relational context does it emerge. The European Space Agency's work on quantum communication satellites explores these strange quantum correlations. By sending entangled photons between Earth and space, researchers are testing the limits of quantum mechanics and probing whether time and space are truly fundamental or just useful approximations. If time is emergent, it also means that at the deepest level of reality, cause and effect might not exist in the way we think. Events don't happen because earlier events caused them. They simply happen, and we perceive a causal structure because of the way entropy increases and information accumulates. This ties back to the arrow of time. In a timeless quantum universe, there is no past or future, only correlations between quantum states. But when you have a macroscopic system with many particles and high entropy, those correlations organize themselves into a temporal sequence. What we call causation is just the statistical tendency for high entropy states to be preceded by low entropy states. NASA's studies of black holes provide another window into time's quantum nature. At the event horizon of a black hole, time behaves strangely. For an outside observer, time appears to stop at the horizon. Anything falling in seems to freeze, never quite crossing the boundary. But for the object itself, time continues normally. It crosses the horizon and reaches the singularity in a finite amount of proper time. This clash of perspectives reveals that time is observer-dependent, a property of reference frames rather than an absolute background. And inside the black hole, where gravity becomes infinitely strong, our equations break down. We need quantum gravity to describe what happens there. And that theory may tell us that time itself dissolves into something more fundamental. Loop, quantum gravity, one candidate for a theory of quantum gravity, suggests that space-time is made of tiny loops, quantum units of space and time. At this scale, time is not continuous but discrete, ticking forward in minimum intervals of Planck time, 10 or 43 seconds. Between these ticks, nothing happens. No change, no motion, no time. This digital view of time is strange but elegant. Just as a digital photograph is made of pixels, space-time might be made of quantum grains. What seems smooth and continuous at large scales is actually grainy and discrete at the smallest scales. So does time exist at the quantum level? The answer seems to be not in the way we experience it. Time, as we know it, is a macroscopic phenomenon, an emergent property that arises when vast numbers of particles interact, become entangled, and evolve toward higher entropy. At the quantum level, there is only a timeless dance of probabilities, a web of correlations waiting to unfold. Take a slow breath. Every second you experience is built from countless quantum interactions, each one timeless in itself. Time is not woven into the fabric of reality, but woven from it, a pattern that emerges when you step back and look at the whole. But if time is emergent, if it's not fundamental, then perhaps we can change it, stretch it, or even stop it. And that possibility leads us to the strangest places in the universe, where time bends, breaks, and sometimes disappears entirely. Part 4. Can time be stopped, stretched, or reversed? Time is not as fixed as it feels. Under the right conditions, it can slow down, speed up, and even come to a stop. This isn't science fiction. It's been measured, proven, and used every day in technology you rely on. The question is, how far can we push it? Can time be stopped completely? Can it run backward? Or is there a limit, a cosmic speed limit, beyond which time refuses to go? Einstein's special relativity, published in 1905, revealed the first crack in time's seemingly rigid facade. He showed that time is relative, not absolute. The faster you move, the slower time passes for you compared to someone at rest. This effect, called time dilation, is real and measurable. Imagine two identical twins. One stays on Earth. The other boards a spacecraft and travels near the speed of light for several years. When the traveling twin returns, she will have aged less than her earthbound sibling. For her, time moved slower. She experienced fewer seconds, fewer heartbeats, fewer moments. This is the famous twin paradox, though it's not really a paradox. It's a verified consequence of relativity. NASA's experiments with atomic clocks on high-speed aircraft confirmed this effect. In 1971, physicist Joseph Haffel and astronomer Richard Keating flew atomic clocks around the world on commercial airlines. When they landed, the clock showed slightly less elapsed time than identical clocks that stayed on the ground. The difference was only a few hundred nanoseconds, but it matched Einstein's predictions exactly. Today, this effect is accounted for in GPS satellites. Each satellite carries an atomic clock that ticks slightly faster than clocks on Earth's surface because it's moving through weaker gravity. Without corrections for both special and general relativity, GPS systems would drift by several miles per day. Every time you use a map on your phone, you're relying on Einstein's equations about time. But time dilation doesn't just happen at high speeds. It also happens in strong gravitational fields. The closer you are to a massive object, the slower time passes. This is gravitational time dilation, a prediction of Einstein's general theory of relativity. Near the surface of Earth, this effect is tiny. A clock at sea level ticks slightly slower than one on a mountaintop. The difference is measured in nanoseconds, but near a black hole, the effect becomes extreme. Time slows dramatically as you approach the event horizon, the point of no return beyond which not even light can escape. According to calculations, if you could hover just above the event horizon of a supermassive black hole, time would pass so slowly for you that hours on your clock could correspond to years in the outside universe. The black hole in the movie Interstellar demonstrated this effect. 1 hour on a planet orbiting close to the black hole equaled 7 years on Earth. This scenario is based on real physics. The European Space Agency's Event Horizon Telescope imaged the supermassive black hole at the center of the galaxy M87, confirming that these extreme gravitational environments exist. Near such objects, time becomes almost infinitely stretched. But can time stop completely? Theoretically, yes. At the event horizon itself, from the perspective of an outside observer, time stops. Anything falling toward a black hole appears to freeze as it approaches the horizon, its light redshifting and dimming until it vanishes. The object never seems to cross the boundary. Time, for it, has stopped. Yet from the perspective of the falling object, time continues normally. It crosses the horizon and reaches the singularity, the center of the black hole, in a finite amount of proper time. This clash of perspectives is one of the most unsettling features of relativity. Time is not universal, it's local, personal, dependent on your reference frame. The James Webb Space Telescope observes matter spiraling into black holes, glowing intensely as it heats up just before crossing the event horizon. These accretion disks are laboratories for extreme physics, places where time behaves in ways impossible to replicate on Earth. But what about reversing time? Can time run backward? In physics, time reversal is a well-defined operation. Most fundamental laws, like Newton's laws of motion or Maxwell's equations of electromagnetism, are time-symmetric. If you reverse the direction of time in these equations, the physics still works. A movie of colliding billiard balls looks just as plausible running backward as forward. Yet, in the macroscopic world, time reversal never happens. We never see a broken egg reassemble or a burned piece of paper unburn. This is because of entropy, the second law of thermodynamics. Entropy always increases, giving time its forward arrow. Reversing time would require decreasing entropy, organizing chaos back into order, and that never happens spontaneously in large systems. However, at the quantum level, time reversal has been demonstrated. In 2019, researchers at the Moscow Institute of Physics and Technology used a quantum computer to reverse the state of a simulated particle, effectively making it travel backward in time by a fraction of a second. This didn't violate thermodynamics because the system was carefully controlled and isolated, but it showed that in principle, time reversal is possible in quantum systems. NASA's studies of antimatter provide another window into time reversal. Antimatter is matter's mirror image, with opposite charge. In quantum field theory, an antiparticle can be thought of as a particle moving backward in time. This symmetry, called CPT, charge, parity, time, is one of the most fundamental in physics. Some physicists, including Julian Barber, argue that time itself might not be fundamental. In his view, the universe is a vast collection of nows, each one a complete snapshot of reality. What we call the passage of time is just our consciousness moving through this landscape of nows, experiencing them in sequence. This idea, called the timeless universe, suggests that past, present, and future all exist equally. Time doesn't flow. We simply experience different slices of a static four-dimensional block. If true, then time travel, in a sense, is already happening. Every moment of your life exists eternally in space-time, and you're constantly traveling through it. But practical time travel, the kind we see in science fiction, remains firmly theoretical. According to general relativity, it might be possible to construct closed time-like curves, paths through space-time that loop back on themselves, allowing you to return to an earlier moment. These require exotic matter with negative energy, something that's theoretically possible but has never been observed in nature. NASA's research into warp drives and wormholes explores these possibilities. A wormhole, a tunnel through space-time, could potentially connect two different times as well as two different places. But keeping a wormhole open would require enormous amounts of negative energy, and even then, causality problems arise. If you could travel back in time and change the past, you'd create paradoxes that physics doesn't know how to resolve. The grandfather paradox is the most famous example. If you go back in time and prevent your grandparents from meeting, you would never be born. But if you were never born, you couldn't go back in time to prevent their meeting. The paradox suggests that backward time travel might be impossible, not because of technology, but because of logic. Some solutions propose parallel timelines, or the many worlds interpretation of quantum mechanics, where every possible outcome happens in a separate branch of reality. In this view, traveling to the past doesn't change your timeline but creates a new one. But these ideas remain speculative, far beyond what current physics can test. For now, the closest we can come to stopping or stretching time is through motion and gravity. Travel fast enough or get close enough to a black hole, and you can experience time at a different rate than the rest of the universe. But truly stopping time, or reversing it, remains beyond reach. Take a slow breath. Right now, your time is passing at a steady rate, synchronized with the world around you. But in principle, if you could accelerate to near light speed or fall toward a black hole, you could stretch that moment, make it last longer relative to the universe outside. Time is not a prison. It's a dimension you can navigate, if only slightly, if only in theory. But if time can be stretched and bent, what happens at the very end, when the universe itself runs out of time? That question leads us forward, toward the ultimate fate of everything that exists. Part 5. Will time end when the universe does? If time had a beginning, does it also have an end? Will there come a moment far in the future when time itself stops ticking, when the universe reaches a state so cold, so empty, so still that nothing can happen anymore? Or will time continue forever, an eternal dimension outlasting even the stars? The answer depends on the fate of the universe, and that fate hinges on three quantities: the universe's total energy, its rate of expansion, and the mysterious force called dark energy. Current observations from NASA's Hubble Space Telescope and the European Space Agency's Planck satellite tell us that the universe is not only expanding but accelerating. Galaxies are moving away from each other faster and faster, driven by dark energy, a force that fills all of space and pushes everything apart. Dark energy makes up about 68% of the universe's total energy. Dark matter accounts for 27%. Ordinary matter, the stuff that makes stars, planets, and people, is only 5%. This means the universe's fate is largely controlled by something we don't understand. If dark energy remains constant, the universe will continue expanding forever, cooling and diluting as it grows. Stars will eventually exhaust their fuel and die. New stars will stop forming as gas spreads too thin to collapse under gravity. Black holes will evaporate through Hawking radiation, a process predicted by Stephen Hawking in 1974, though it takes an unimaginable amount of time. After 100 years, give or take, the universe will reach a state called heat death. All energy will be evenly distributed. No temperature gradients will exist. No flows, no changes, no events. The universe will be a uniform, cold, dark expanse, hovering just above absolute zero. In this state, entropy will have reached its maximum. There will be no low entropy pockets left to drive processes, and without change, Without events unfolding, time loses its meaning. Physicists debate whether time would truly end or simply become irrelevant. If nothing can happen, does time still exist? According to Carlo Rovelli, time is change. Where there is no change, there is no time. In the heat-death scenario, the universe doesn't stop existing, but it stops evolving. Time, in any meaningful sense, ends. But heat death is not the only possibility. If dark energy strengthens over time, the universe could end in a big rip. Galaxies, stars, planets, atoms, everything would be torn apart by accelerating expansion. Even space-time itself could be ripped to shreds. In this scenario, time would end abruptly, destroyed along with space in a final violent unraveling. Another possibility, though less likely, given current data, is the Big Crunch. If the universe's expansion slows and reverses, gravity could pull everything back together into a singularity, a mirror image of the Big Bang. Time, which began at the Big Bang, might end at the Big Crunch, the universe collapsing back into a state where space and time cease to have meaning. Some cyclic models propose that after the Big Crunch, a new Big Bang could occur, creating a new universe with its own time. In this view, time is reborn with each cycle, though whether it's the same time or a new one is unclear. NASA's studies of cosmic expansion are narrowing down these possibilities. The discovery that expansion is accelerating, confirmed by the 2011 Nobel Prize in Physics, rules out a Big Crunch in the foreseeable future. The universe seems destined for eternal expansion, but quantum mechanics adds another twist.